Welcome to this AOS-CX 10.12 1000 update. My name's Steve Bartlett, Technical Marketing Engineer supporting Aruba CX switching, and this update is around the IPsec feature with the Pensando PSM and the CX 10,000. And this is the agenda. There's 5 topics: the overview, use cases, details and caveats, configuration and scalability at the end there. And if you're very familiar with the background in IPsec, then obviously do feel free to skip the overview, but I would recommend you go through the use cases and the details and caveats before you get into the configuration topic. So straight into the overview section. So IPsec, it's been an established technology for many years now, and I'm sure many of you would have encountered it at some point, either directly on firewalls or with encryption cards on routers and servers. So if you've been away from the technology a while, so this will be a quick overview to remind us all of what it is and the key building blocks on how it works. So a bird's eye view, there are 3 main IPsec protocols. First is the IKE, the Internet Key Exchange, which establishes an SA, a security association between 2 devices, and thereby negotiates the cryptographic and keys and algorithms that will be used for the duration of the session. And then we have the authentication header, AH. This adds a header field to the packet sent, includes the crypto hash of the packet's contents so that the receiving device can use the hash to ensure the payload hasn't been modified. And then we have ESP, encapsulating security payload, encrypts, adding a sequence number to the packet header. And within IPsec itself, it supports a broad range of encryption technologies with the supporting protocols, and it has been very popular since it was first introduced in the 1990s. So drilling down to a bit more detail with the overview of IPsec. So there are 2 different modes for IPsec, transport mode and tunnel mode. So transport mode, typically used for a workstation or client server host to a gateway or a host-to-host communication. Transport mode will encrypt the payload only, not the header, and leave the existing packet header more or less intact. And then there is tunnel mode. Now tunnel mode is where IPsec creates an entirely new packet header and encrypts the original packet header and its payload, which becomes the new payload for the new packet with its new header. And the CX 10,000 with the PSM support supports tunnel mode only. So IPsec uses 2 key protocols to provide traffic security: authentication header and encapsulating security payload, ESP. ESP offers the same set of services as AH and also provides confidentially, as it encrypts the internal IP header as well as the payload, and is generally the preferred option. So from a standard RFC perspective, IPsec must support ESP, but it may support AH. And the PSM CX 10,000 combination for the release supports ESP and not the AH protocol. So an overview then of the IPsec protocol framework, which is supported with the PSM and the CX 10,000. The supported items are highlighted in green. So first up is IKE, Internet Key Exchange V1 and V2. It's a tunneling protocol that establishes a secure VPN communication between VPN devices and defines negotiation and authentication processes for IPsec security associations. So V2, better than V1. V2 supports more features, faster, generally more secure. So V2 is preferred. Then we have the IPsec protocols themselves. So ESP, the support for this is mandatory, and that's what's supported for the PSM and the CX 10,000 combination. And different encryption standards are supported with variable options like AES, triple DES and CAS 128. and along with hash algorithms are supported with SHA, the security hashing algorithm, with options for SHA-256, 385 and 512. So SHA provides better security than MD5. And lastly, public key encryption is provided by the Diffie-Hellman suite of protocols for the key exchange to establish a secure connection between endpoint clients. Now on to IPsec implementation. So there are several ways to implement IPsec. So it can be integrated into the native stack with source code, bump in the stack, use of a dedicated inline security appliance, which most networking folk I'm sure will be familiar with, and the CX 10.12 aligns to this model. And the IPsec flow is terminated on the Pensando Elba P4 CPUs within the CX 10.12 using a dedicated encryption chip. The IPsec tunnel itself is exposed with the AOS-CX CLI for configuration purposes, and as I mentioned earlier, the CX 10.12 supports tunnel mode only. So from a very high level, of course, if we take the original IP packet prior to encryption with IPsec encryption with ESP, with tunnel mode using the CX 10.12, this is what the packet format will look like. The original IP header is now encrypted along with the payload and with the ESP trailer added, and an outer ESP header is added with a new IP header containing the source and destination of the tunnel endpoints. Moving on to use cases now, and there's 3 to take a look at. So use case 1, a classic deployment model between sites, in this case, in this example, DC1 to DC2, and there's an encrypted IPsec tunnel between the border leafs, and that's encrypting the data between DC1 and DC2, and this will provide a secure connectivity between the data centers. So a classic model that probably we're all familiar with. Use case 2, private cloud, colo and hybrid cloud, and this requirement is increasing in popularity with customers who have similar cloud models and wish to ensure secure communication to the cloud, whether it be private, colo or hybrid. So what we have standards-based encryption with IPsec, 200 gig full duplex throughput, and we've got encryption from the border leafs to the remote IPsec gateway. So here we are, from the border leaf edge of the data center, the colo, private cloud and HP GreenLake, all this providing secure connectivity from on-premise to off-premise, whether it be public or private or hybrid clouds. So use case 3, site-to-site IPsec offload via the internet. So the benefit of this is to offload some or all of the IPsec traffic from another device. In this example, it's a perimeter-based firewall, providing potential cost savings and potentially increased throughput of IPsec traffic due to some throughput constraints. So how this would work is the external facing firewall with NAT translation enabled will still be in place, providing perimeter firewall security features. So incoming traffic from the internet traverses the internet through the external firewall to the CX 10.12, where the IPsec encrypted traffic terminates and is decrypted. And then the unencrypted traffic is directly returned to the perimeter firewall for inspection. And then the inspected traffic is returned back to the CX 10.12. So all this provides a secure connectivity model back into the applications located in the data center and potentially alleviating the IPsec burden on the external firewall. Moving on to details and caveats. So an overview of the IPsec feature. So the first part is the IPsec parameters are all configured via the Pensando PSM. The tunnel endpoints for the IPsec tunnel do terminate in the Pensando P4 processors, but they're presented in the CLI for ease of use within the AOS-CX software. High availability options, there's three. There's IPsec active-active. This is generally the recommended option. Each endpoint client, this would be the client being the switch network device. In this case, a VSX switch pair has two active tunnels to the destination CX 10.12 VSX pair, one active tunnel per VSX switch. And the tunnel endpoints are unique SVIs, and they're derived from the active forwarding IPs on each VSX gateway. And then we have IPsec active standby AS, the legacy option for endpoints, the clients that support only one tunnel, and there's only one active tunnel to the CX1010 pair. At the other end, if it can't support active-active, it would have to support at both ends the VRRP protocol, and the tunnel endpoint is the VRRP SVI, and it's mandatory to run VRRP in this mode for active standby. And no HA, this means there's just a single tunnel only. So IPsec will work with or without NAT enabled. So incoming traffic, so that's DC outside the DC going to DC inside, goes through the IPsec decrypt engine, through the firewall engine, and then optionally through the NAT engine. Outgoing traffic, so it's from DC inside to DC outside, is firewall engine first, then NAT, optional of course, and then to the IPsec encrypt engine. So this is applicable only on border leaf devices and not on host leaf devices. So this is assuming you've got a spine leaf fabric. A quick overview then of the IPsec option in a bit more detail for encrypt decrypt directions. So there's no specific policy direction for IPsec. The IPsec operation direction, the operation is done for all clear unencrypted traffic exiting the DC, meaning that everything destined for the IPsec tunnel is encrypted, and likewise the decrypt operation is done for all encrypted traffic entering the DC, which is effectively leaving or exiting the encryption tunnel. An explicit firewall policy is not mandatory. An implicit firewall policy is permit all for if no explicit policy is applied, so you don't actually have to explicitly apply a firewall policy. NAT, of course, is optional. So just from inside DC to outside, we've got a persona access port, hits the firewall engine should there be a policy applied there. Then the NAT process optional, and then the traffic is encrypted down the tunnel with the encryption engine prior to that, and goes out a persona uplink. Coming from outside the DC, we come from into a persona uplink into the IPsec decrypt engine through the firewall engine to apply a policy or not, depending on how our firewall inspection is configured. And optionally, we can configure NAT, and the traffic leaves into the inside of the DC via a persona access port. Just a couple of points down here, the CX10,000 switch profile, which is a CLI configuration, it has to be layer 3 core or spine. Just make a note of that. So a bit more detail on the IPsec process. So IPsec tunnels can only be established if the switch is running either layer 3 core or spine profiles, as I mentioned in the previous slide. The tunnels themselves, IPsec, must not be configured within the default VRF. It will not work. So a specific VRF is required. IPsec tunnels are not supported either with routed only ports or loopback interfaces and underlay. So that just leaves us with the option of IPsec tunnels supported with SVIs as integrating into the underlay as the source of the tunnel endpoint, and the IP address for the tunnel must be derived from the underlay SVI. And we'll see an example of that in the configuration example that I've got in a few slides down. VXLAN over IPsec is not supported. Now VRF, now when I say supporting end host client by the persona access, this VRF here, and the northbound VRF containing the persona uplink, supporting the uplink SVI, including the tunnel interface, these must be on the same VRF, and that will be as part of the configuration example I'll show you later. And lastly, the three modes of HA, no HA, active is obviously the recommended, and active passive. And another reminder, switch profiles, layer 3 core or spine at either end of our tunnels. So taking a look at the topologies for active, this is generally the recommended option should it be available. So assuming that both endpoint devices can support active tunnels, then this is the way to go. So we've got tunnel 1 on a VXX switch 1 and tunnel 2 on VXX switch 2. They've got different source IP and destination IPs, as you can see, which are reflected on vice versa at the remote site, and there's 2 active tunnels with iKey active set up to get those tunnels up and running. And effectively traffic can be load balancing with multi-chassis link aggregation at the edge here to go down and load balance across the tunnels. So that is the topology that's recommended. So ideally VSX at the other end, but any supporting endpoint device that will support active will work. Next up, active standby topology. Typically we'd refer this to as legacy clients, and this has to use VRRP. So VRRP will be active and standby, and there'd only be one tunnel active at any time for encrypting and decrypting, and if one endpoint failed, then it would fail over as part of the VRRP process and re-establish the tunnel as part of the standby link. So I'll just run through some caveats, and these are effectively unsupported features that will not coexist. Some unsupported features will obviously impact networks more than others depending on the environment, but I've highlighted some of the more common ones, the caveats that may impact general network topologies. So first one up is VXLAN encapsulation over IPsec is not supported as part of this release. Same with IPsec tunnel endpoints as IPv6, that is on the roadmap, but it's not here yet. Underlays on different VRF, so these are not supported features. We've got the underlay and the access VRF has to be on the same VRF. No dynamic routing over IPsec tunnels, and another one to be watchful of is multicast over IPsec tunnels, but do take a look at these to make sure you don't actually get called out. ACLs on the IPsec tunnels, well, less of an issue really, because we've also always got the firewall inspection engine for our traffic ingressing and egressing our data centers, for instance. And just to finish off the caveats, northbound or southbound VRFs, as I mentioned, need to be the same for the initial release. No VRF leaking between the southbound VRFs. Multiple tenants will require a separate northbound VRF uplink matching the southbound VRF. So if you've got a separate tenant, you're going to need to spin up another VRF for that tenant. Now moving on to configuration. So this is configuration guidance for IPsec. So first one is obviously configure the switch tunnel endpoints. Ensure the underlay connectivity between the tunnel endpoints is there. I mean, that's basic network common sense, of course. And ensure MTU size within the transmission path is appropriate to support the IPsec encrypted packets and jumbo frames if they are desired. So it's an easy one to be called out on if the tunnels don't come up. And on the configuration side, static routes for target subnets to use appropriate interface tunnels. and ensure the CX10 switching appliances are configured for layer 3 core or spine profiles, and uplink interfaces to use the persona uplink profile, layer 3 uplinks to use layer 3 SVIs. We'll cover this in more detail in the configuration section, actually on the CLI. The external border leaf support only at the edge of a fabric. VXLAN encapsulation is not supported with IPsec, and you can only run the IPsec out of the border leaf, not at the top of rack leaf. So that's got to be clear on that. Do not use the default VRFs. It does not support IPsec. And ensure host-facing and network-facing VLANs. So that's host-facing the client with a persona access, and the network-facing, which is the persona uplink, are allocated to the same VRF. Obviously, that is local switch endpoint significant. You can have separate VRFs at the destination endpoint. So do use the policy distribution targets within the PSM. The good practice for granularity. So that's a good practice in general. So all IPsec policies are configured within the PSM, and apply firewall policies as desired or needed. So a quick summary of the failover options. First of all, there is active. So this is no failover as both tunnels are active. And then we have active standby using VRRP at one or both ends. That's the option, and you need to use VRRP if you're using active standby. And the tunnel source is the VIP of the VRRP, and the IX session is only to the active VIP address on VRRP. Of course, you can have no active standby or no active with just a single tunnel, of course. So this is an example of the configuration with active tunnels, which the subsequent PSM configuration, the example slides that will come up after this slide, support the same deployment. So let's take a look at this. At DC1, there is a CX 10.12 VSX pair. We've got a VSX primary and VSX secondary supporting VLAN 200, and attached to VLAN 200 we've got a host A on subnet 10.200.200.0. Note the MTU size applied to all interfaces between host A and host B. That's increased to support the expanded IPsec frame size, and of course jumbo frames if you need it. So at DC2 we've got a similar identical configuration. We've got VLAN 201, active VSX 10K pair, VSX active gateway configured, VSX primary, VSX secondary, and that connectivity model effectively reflects the same at DC1. Now moving on to the active tunnels at DC1 switch 1. So we've got configuration of interface tunnel 1, mode IPsec, source IP address is 192.168.254.2, targeting destination IP 192.168.254.10. And I hear you say, where do we get these IP addresses from? And here would be the explanation. So the source IP address of 192.168.254.2 at DC1 switch 1 for that tunnel 1 is derived from the interface VLAN 2000, which is the northbound VLAN connecting to the layer 3 network, and call it the underlay to support the overlay transmission of the IPsec connectivity. Now that subnet needs to be large enough, as you can see I'm using a /29 to support active forwarding, and it has to be configured, this VLAN, for active forwarding if you're using active tunnels. It cannot be active gateway, it has to be active forwarding. So that's how we derive the source IP tunnel address of 192.168.254.2 from that active forwarding VLAN on 2000 for DC1 switch 1. Likewise at DC2 switch 1, interface tunnel 1, source IP 192.168.254.10, which is the destination IP here, is derived from its northbound VLAN 2001 connecting to effectively the Layer 3 transmission network using active forwarding, as you can see here. So that is the source IP address of DC2 switch 1, and that of course makes our source and destination endpoints for our tunnels in our local configurations on the appropriate switches. All well and good so far. So we must use, as I mentioned, for VLAN 2001 and 2000 as these northbound connectivity VLANs, we must use active forwarding and take the IP address for our source IP addresses for our tunnels locally at each local switch. In addition, we need to configure our target routes to use the local tunnel. So at DC2 we have a IP route 10.10.200.0, which is where host A sits at DC1 to use the local tunnel 1. And the VRF is obviously using, I've called it IPsec services. And at DC1, switch 1, I've used the same method, IP route 10.10.201.0 subnet, which is targeting host B to use that local tunnel 1 that's on DC1, switch 1. All well and good so far then, hopefully. And these subnets locally, VLAN 200 and 2000 is an example, which is the host VLAN, and the northbound VLAN must be used the same VRF. Absolutely must use the same VRF. This is on the first iteration of our IPsec deployment, and we're looking to change that in the future, but today this is the constraint that we need to articulate. And of course, you can use the same VRF or a different VRF with local significance, of course. So the same policy methodology applies to DC2 as well. For VLAN 2001 and VLAN 201, they must use the same VRF, which of course can be different to the target destination host VRF. Now on the other VSX pair, DC1 switch 2 and DC2 switch 2, we use the same concept to configure the tunnels using VSX active forwarding IP addresses. Note obviously the tunnel addresses are different. They're on the same subnet, but they are different. So don't forget, this subnet needs to be large enough to support active forwarding on the same VLAN across the VSX pairs. So do be aware of that. And we've got our source and destination tunnel addresses, 4 different IP addresses, 2 tunnels, source and destination pair, targeting each tunnel appropriately on each switch pair at our source and destination locations. Moving on to the PSM configuration for active tunnels. So first of all, first step is to create the desired VRF in the PSM and ensuring it is present on the target DSS switching. Now, the interesting point about this process is that the VLANs that are assigned to the VRF on the switches will inherit the VRF allocated policy. So what within the PSM. So what I mean by that is once you create a policy, then allocate it to the VRF within the PSM, the VLANs will be redirected to the DSM dynamically. You don't have to manually redirect them. And then you create the appropriate policy distribution targets. So these are effectively, in this example that I'm going to show you, will be the DC1 switch 1 and switch 2 pair and DC2 switch 1 and switch 2 pair. And basically the distribution targets are a collection of DSSs that can be used to specify which switches inherit a given policy. So that gives a bit of granularity to the way we deploy policies within a PSM fabric. And then we create an IPsec policy, and this is the steps that I'm going to display in the following slides. So on to PSM policy distribution targets. Now, quick note about VRFs. I haven't shown you a slide for creating VRFs, but one note that you do need to be aware of if you're not familiar with it is that the VRF name, when you create a VRF within the PSM, it must match the VRF name that's already configured on the CX 10.12. So when you create a VRF in the PSM, it doesn't get pushed down to the CX 10.12, but the naming convention, either using upper and lowercase mix, must match the name that you're using of the VRF that are already on the CX 10Ks. So we're going straight into PSM policy distribution targets, and you find them under tenants, policy distribution targets. And if you're using it for the very first time, you've not created a policy distribution target in that fabric, you'll find that all the CX 10Ks are in effectively a default distribution target. So you scroll down, select one by one the 10,000 switches that you want in that policy distribution target. I've selected 2 here. These are, can't see the name, but it's DC1 switch 1 and DC1 switch 2, and I've called it DC1 IPsec and save it. And I've done exactly the same for the DC2 site as well. I'm creating another policy distribution target, done exactly the same thing, select the appropriate switches, DC2 switch 1, DC2 switch 2, and created the name and saved that as well. The reason I've created 2 targets is because there will be 2 IPsec policies, a separate one for DC1 IPsec and a separate 2 for the site 2 DC2 IPsec as well. So that's why we've got 2 different targets to support 2 different policies. Creating a IPsec policy is very straightforward. From tenants, select IPsec policies and then select add from the tab, and you will get a menu to complete. Now obviously this is a snapshot of a policy that I completed earlier, and the prerequisites in the fields will be highlighted in red, and they are effectively the ones that you can see that are already completed. So at the very top, you obviously got the policy name, the policy distribution targets that you are selecting, and if you select that, you then get effectively in the menu here options of the various switches within that policy distribution target to select. The HA mode, active active, active passive, and no HA for a single tunnel are the options. And then you come into your various configuration options, starting from general, as you can see, the tunnel name, the IC version, and the DSS that you want to select from that policy distribution target, which, because there's only 2 switches, when you drop down onto that, there'll be just the 2 options to select. So this is actually DC1 switch 1 that I'm selected there. IC SA parameters, IPsec SA parameters. At one end of the tunnel, you need to select an IC initiator for that particular tunnel switch. Because we're using active, there's going to be 2 tunnels, so then you will then get the option to select the second switch to set off the other active switch tunnel, and this will be DC1 switch 2. Again, that will be an IC initiator to keep it uniform at one site. And that is it. They're the options that you configure. You can see there's lots of options for the parameters from IC SA and IPsec SA parameters to choose from. Obviously they need to be uniform at either end, but you've got the options to use in terms of the encryption algorithms, hash algorithms, etc. to use. There's options there. And that is effectively the configuration for one site, and this is DC1 site. And for site 2, you effectively repeat the process. So you can see that the parameters are identical on here, except the IC initiator, which is turned off because we're using the DC1 site to actually be the initiator for both tunnels. So these are the parameters for one tunnel, and this is a parameter for the other tunnel. So the last part of the configuration, the last step, is to align the IPsec policies, or the appropriate IPsec policies, to the VRFs that are being used. Very simple activity. So from tenants on the main PSM user interface, select VRF, and from there then select the appropriate VRFs that are being used. In this case there's only one, IPsec-services in this example, and then from the pencil edit you get the option. If you just roll down to the IPsec policy tab, select that, then it will give you the options of the IPsec policies. And of course we're using two IPsec policies for that VRF, DC1-IPsec for DC1 and DC2-IPsec. If there's two VRFs that are being used, one at either site, then you need to align the appropriate IPsec policy to each VRF for that site. Once that's complete and saved, then from the VRF overview menu, you get the option, obviously, of seeing the IPsec policies aligned to the appropriate VRFs. And here you see them, DC1 IPsec, DC2-IPsec for those two IPsec policies for that particular VRF. As I mentioned earlier, VRFs have VRF granularity for the spine and layer 3 core switch profiles, which you need to use for when you're using IPsec. So this means as I mentioned, associated attached VRF VLANs configured in the switch are redirected automatically to the DSM when the VRF matching on the switch is configured on the PSM because of this VRF granularity. Conversely, layer 3 AG and leaf switch profiles have VLAN granularity. VLANs are then manually selected via the PSM to be redirected to the DSM, and we do that via the Networks tab here. But we don't need to do that if we're using VRFs and IPsec and the spine and layer 3 core switch profiles that are configured on the switch. So the next step is then to check the tunnel status as part of the IPsec policies. So that's very easy to do. From tenants, we go back into IPsec policies, and what we should be expecting is that at each site, DC1 and DC2, two tunnel endpoints at each site, they should all be up, and that is the case in this example. They're notated with the up arrow. So that's all looking healthy, and the next step of course would be just to make sure that you have the appropriate connectivity between the endpoints to be sure. For diagnostics and to see the status of the tunnel, you could just go into the CLI and do show interface tunnel 1, for example, to get the status of the interface. That would be okay. But for a little bit more information, you can go into the PDS-CTL to actually do a status of the show tunnel, and we access that from diagnostics, diag DSM, to connect to the appropriate DSM console. In this case it's 1/1, and then do PD-CTL show tunnel. Gives us a little bit more information with local IP and remote IPs, and of course the admin state of the tunnel, which is up, and the tunnel role, which is active. So this is just a snapshot of one of the IPsec encrypted packets, so you just see what it looks like. Well, there's not much to see really, but you do get the source and destination tunnel endpoints, and of course everything from that point on is encrypted as part of the encapsulating security payload, ESP protocol, and effectively this part would be unreadable because it's encrypted, and that's the encrypted payload. So that's the type of information you expect to see within a IPsec encrypted payload. And the last part of this presentation is scalability. So the IPsec performance is very, very, very good. as you can see, per CX 10.12, you actually get 400 gig of throughput. So that's 200 gig of encrypt, 200 gig of decrypt, and that's 200 gig of full duplex transmission throughput, and that's 100 gig full duplex per DSM. So very, very strong throughput figures for each 10K. Well, that brings us to the very end of this presentation. I do thank you for tuning in, and I do hope that this presentation has been useful for you. Thank you.